This video will show you how to install the sparselizard finite element C++ library. It will also show you how to run a very simple test case to ensure everything's working as expected. Now the first thing to do is to go on the sparselizard.org website. Where you will find everything you need to run and use sparselizard. So you have an overview of what it is. You have a couple of examples on what it can do. So this is a subset of 3 examples of what sparselizard can do. So here, for example, it shows how to simulate electromagnetic waveguides, so wave propagation in these waveguides. And you have an example. So if you click here, you will get the code. And if you just copy paste the code, you will be able to simulate this electromagnetic 3D waveguide. Now you also have an install section where all the steps to install sparselizard are detailed. So we will do this in this video, but here are all the steps you need to install sparselizard otherwise. The first thing to do is to download the library on my desktop, to extract the archive, and there you go. Here's the library. Now let's open it in the terminal. Everything's really similar when you use Mac. Here I'm using Ubuntu Linux. You can see in the folder that you have the install external libs folder. This folder has a couple of shell scripts that help you install all the external libraries required by sparselizard with the appropriate configuration options. So this script installs the OpenBLAS library, which is used for efficient and parallel dense matrix operations. This installs the FFTW library for Fourier transforms. This installs the PETC library, which mainly does operations on large sparse matrices, and in combination with MUMPs, it solves these large algebraic sparse problems. And this installs the SLEPC library, which is used for eigenvalue computation. Now, if I was to install OpenBLAS, for example, just go in the install directory, and then you install OpenBLAS by running the script. I will not do it because it takes quite a while, about half an hour to install the 4 scripts. Everything should work fine. If it does not, just open the script and you will find all the information you need, like here for PETC, the configuration options that you need to have it working properly with sparselizard. Otherwise, if you don't have any problem, running this one, followed by this one, and then this one should install all the libraries correctly in your home directory in the SLLibs folder. Now let's move one level up. And suppose we have the external libraries installed correctly. Now the next step is to actually compile sparselizard. You do this with make. Here I have 4 processing units, so I do make -J4, and then it's compiling sparselizard in this build directory. This takes about 5 minutes on my machine, so we can do something else in the meantime. We can see the problem we will simulate to see if everything's working fine. So we will simulate this main CPP file using this disk.geogeometry file. Now this geometry file is a GMesh geometry format, and we will use the finite element GMesh meshing software to mesh it. So we go to the GMesh web page and we download the GMesh binary here for Linux. We download it in the same folder. It's relatively large, and in the meantime you can have a look at the web page. So GMesh, it's a widely used open source general meshing software in 1D, 2D or 3D with a lot of documentation and a lot of tutorials. So creating your own geofile geometry should be relatively easy. Now the download is over. We can extract the binary from the archive because we're only interested in the binary here. There you go. And we can mesh the geofile. So for this, we open another terminal and we run gmesh with disk.geo. We open this and we see our very simple test case. It's a relatively thin cylinder, a 3D. We can mesh it in 3D like this. And in this cylinder you have a couple of regions defined. You have the volume region, which has number 1. You have the external surface, which has number 2. And you have the top surface, which has number 3. So when I mesh it in 3D here, and I save the mesh, it writes a .mesh file, which knows the region numbers 1, 2, and 3. Now, you could wonder why we use only so few hexahedra. We will simulate a mechanical deflection when the circle here, circular surface around, is clamped and you apply a volume force pointing downwards. Now, you might want to put more elements to have a more accurate resolution. You can do this by clicking on Refine by Splitting if you want to. This will work easily. sparselizard can handle a few 100,000 to 300,000 hexahedra in 3D for mechanics, or a couple of million of quadrangles in 2D without any problem. But here the goal is to simulate the disk deflection using very few hexahedra but with a high interpolation order. Now there's one last thing. Here in this particular case, the boundary is circular, and you see here with so few elements you don't have a great approximation of the circular boundary. You have a straight line interpolation here. Now, without increasing the number of degrees of freedom and the number of elements, you can just use curved elements by clicking on, for example, set order 2, and this will give you a much better approximation of the circular geometry. You now save the mesh, and now you see a new mesh file here appearing. This mesh file includes all the node coordinates in your mesh and all the elements, the hexahedra and elements. Now, in the meantime, sparselizard has finished the compilation, and we can run the main.cpp file by executing the run sparselizard script. Now it's done. This has created the u.pos file where you have all the output thing you want to visualize. So here you have the deflection on the top surface of the disk. This file you can open with gmesh simply by calling the binary you've downloaded and open it with gmesh. Now you don't see anything. This is not an issue, it's just that you used curved meshes and gmesh complains because it cannot just like that display the deflection. What you have to do is double click, go to all view options, general, tick the adapt visualization grid box, set the target visualization to a minimum value, and increase the maximum recursion level, for example, up to 4. But don't exaggerate this. We can also remove the color, and since it's a mechanical deflection, we might want to see it as a mechanical deflection, like this. And there you go, you have your mechanical deflection, exaggerated, as we will see right now. Now, what does the code look like? It's in main.cpp. You first include all the headers required for sparselizard. You use namespace math_up because a lot of calculations, for example, here the TF is defined in math_up, and if you don't want to always call math_up, you might want to set this line so that the default library used is default namespace used is math_up. Now you also have your main, which is mandatory, C++, but this only calls the sparselizard function. So in the end, the only thing you have to edit is this sparselizard function. And what do we see in this function? The first line corresponds to giving names to the region numbers. So remember, in the geofiles, we defined regions. So the volume region was number 1, the external surface was number 2, and the top surface was number 3. So in order to avoid using numbers, we just give them names. This is more convenient. And then we load the mesh file by creating the mesh object. We also define the mechanical deflection field U, which is a classical mechanical deflection field. So it uses shape functions h1. These are just classical nodal shape functions. But since we have 3 components, we have to specify that it's a vector nodal shape function with 3 components. So thus h1, x, y, z. Now we set order 3 on the whole region because we just have 1 region. If you had 2 regions, you could choose to set order 2 on one and 3 on the other. This is no issue because we use hierarchical shape functions, so you can combine different orders for different regions or for different fields. Now we constrain the deflection on the external surface to 0, so we clamp the disk, and this is just done with this line. Now if you don't have any value, it means it's considered to be 0. Now this would work as well, but it's not required here, since if you don't put it, it will be 0 anyway. And then we define parameters. So here E the Young's modulus, nu Poisson's ratio, and we set the parameter value on all the regions we're interested in. So here only one on the volume. We set it to polysilicon values, and we set it using this straight bar. We define the elasticity formulation, which will be the weak formulation of the classical linear elasticity problem. Since it's classical, it's predefined, so we just call this. And we have to add to that formulation a term which corresponds to the volume force in the minus z direction, this term. Tf is the test function, dov, which is included here, is the unknown. Here it's a right hand side contribution, so you just have the test function. Then we generate the problem. This will create and assemble the A matrix and B right hand side vector in the AX equal B algebraic problem to solve. We solve this problem. We get the solution SOLU. It's a solution vector. Now we want to be able to visualize the deflection, so we will have to first transfer data from the solution vector to the deflection field U with the setData function. So this takes all data in the vector SOLU on region vol and puts it in the field U. And then we just save the deflection to disk. So you can write any expression here. You could write u times u if you want, if it makes sense. Here we just write the deflection with an exaggeration factor of 500 million. We write it on the top surface, so this will be quadrangles, and we write it to the u.pos file with an order 3 interpolation, because we used order 3 interpolations. If we remove this, we will have an order 1 interpolation and our solution will be much less accurate in terms of visualization. So you will only have linear interpolations. Now, what if you want to simulate this? As we did before, you run this and then you plot the solution. We get a maximum deflection of 0.583. And what if you want now to edit the main file to increase, for example, Young's modulus to 200 billion? Now you edit this, you save the main file, and then you have to compile again the project because the main file changed. But since only the main file changed, the compilation will be much faster, so you run make. And then you run the sparselizard script again. We open it, and what we expect, because we have a stiffer material, we expect a lower deflection. And this is indeed the case. The maximum deflection is 0.437. And the shape does not change. There is no reason. It still looks the same. Just that the deflection is a bit smaller. Now, thank you for watching this video. If you want more examples on how to run sparselizard and how to use it, just have a look at this example folder where you will find a lot of examples with a lot of comments to what every line is doing. Thank you very much for your attention. See you at the next video.